Hi, everybody. These are the notes for the law of universal gravitation practice problems. There's 4 little problems that are on a worksheet. And the first problem, actually, it's more like the second problem is the one that's going to be more like the one on the midterm. And the first law you see up here, word for word, is going to be on the midterm. And what it says is this, that the force of gravity is directly proportional to the product of the masses of 2 objects. So here's what that means. If I weigh more, that means Earth is going to attract me with gravity more. So if I weigh twice as much, what happens to my weight? It goes up, okay? By how much? Twice. So you have twice as much mass, you have twice as much weight. Okay? If the Earth was twice as massive, what would happen to my weight? It would go up by twice. Thank you so much, Vincent. He is on the ball today.
Yeah, he is.
Now, the other thing it says is that gravity is inversely proportional to the square of the distance between the 2 objects. So what this means is the farther I get away from the center of the Earth, what happens to my weight? Very good. It goes down. Great. So this whole thing ends up being called the inverse square law. And you're going to find the inverse square law in every form of forces that you can possibly have. So in electromagnetic forces, you'll see this law. In nuclear stuff, you'll see this law. Actually, in gravity, you'll see this law. And so since all these forces have the same type of formula, Newton thought what? Or Einstein thought what, rather? They were all related in the grand unification theory. So let's go through now and discuss what we have here. If I were to write a mathematical formula for this now, I don't know why my eraser just happened, okay? I'm going to have F sub G, which stands for the force of gravity, which is also the same thing as my weight. And instead of making an equal sign, let me make a proportional sign first. To the product of the masses, which means mass 1 times, oh, biscuits. Shoot. Stop. Okay, mass 1. Yeah, that didn't work. All right, we're going to try this again. So I'm going to have the mass 1. It didn't work. Let's try this again. So I'm going to have mass 1 times mass 2 divided by, now that's where it says the product of the masses. It's proportional. Now the next part says it's inversely proportional. So where do you put that? Very good, on the bottom of the fraction, to the square of the distance. So I'm going to have something that looks like this. Okay. So let's just pretend that all these numbers were 1. So I got 1 times 1 divided by 1 squared. What's that all going to equal? 1. Congratulations. Now, if I double my mass, though, now I'm going to have 1 times 2 divided by 1 squared. So what happens when I double my mass? I double my force. If you triple your mass, what happens? You triple the force of gravity. You triple the weight. But watch what now happens if you put in distance. So now I'm going to have everything as 1 again. But now I'm going to double my distance. Well, that distance is squared. So instead of 1 over 2, I have 1 over. So now you have, if you double your distance from the center of the planet, you now have 1/4 the gravity. If you triple your distance from the center of the planet, you have 1/9 the gravity. And so this is what we mean by the inverse square law. As one thing goes up, as distance goes up, force goes down by the inverse square. Guys, let me go and talk about something else. There were some guys that actually proved this to be the case. And their names were Cavendish and Henri. Cavendish, I can never remember how to spell his name. But Cavendish, what he had was a huge sphere. Let's see if I can draw this. This would be incredible if it works. So we had this big, hey, that's a big old sphere. So we have a big old sphere here of lead. And took another little sphere. I'm not sure what it was made out of. But he hung this one from the ceiling. A little teeny one. Now, what's the big sphere going to do to the little sphere? Pull it, because once again, it has a big mass, so it's going to have a certain amount of gravitational force. And what they were able to do is with some scales up here, they were able to hang this from a scale, they were able to measure the force, and they knew the mass of this one, and they knew the mass of this one, and they also knew the distance between them. Well, you know how I said that these things are proportional, right? Well, what they found out is there is a constant that makes them equal. And that constant is what we call big G. So now to make these things equal, I'm going to have gravitational force equals G times M1 times M2 divided by B squared. Okay? And this is Newton's law of universal gravitation. And what they found out is that this G is very satanic. It's actually equal to 6.66, but they rounded it up to 6.67 because they didn't want it to be satanic. And then it's multiplied times 10 to the negative. Now it's negative because hell is below the ground, and so therefore, and then it's negative 11 because it looks like a pitchfork. Make sure you know that for the midterm exam. Hint, hint. Okay, 6.67 times 10 to the negative 11. So what we're going to do is now, think about this. We can measure the weight of the Earth. If I know my weight would be my force. If I know my mass, and I know my distance from the center of the Earth, I can now weigh the Earth. So let me show you how they did that. Let's go down to the first, or the number one on your worksheet there. It says Mr. Wright weighs 980 newtons. So going back to this, my weight or my force of gravity would be 980. The mass of me, that's a me down there, is 100 kilograms of PMM, that's pure muscular mass. I'm looking to find out Murph, which is the mass of the Earth. And then the distance or the radius of the Earth is 6.38 times 10 to the 6 meters. So let's plug all this into a formula now. Don't forget the formula is going to be F equals big G times M all divided by B squared. What are you going to put in for G? Very good. 6.67 times 10. I got ahead of myself. Times 10 to the negative 11. Thank you so much, Megan. I got ahead of myself. I should put in F. And like Megan said, it was 980. Thank you. And then I'm going to put in the mass of me, which is 100. I'm looking to find out the mass of the Earth. And I'm going to divide that by its radius squared, so 6.38 times 10 to the negative, times 2 to the 6 rather. And don't forget what you got to do that distance. And that's the big mistake that most people make on their tests is they forget to square that. And so when you do all the math here, I end up with Murph equal to, here we go again. Stop! 5.98 times 10 to the 24th kilograms. Okay, so we're recording. What's my weight on the moon if my mass is 100 kilograms? So I got my M up here. That's not working. Let's try this one. Oh, that's perfect. So that's the mass of me. The mass of the moon is given to you here at 7.35. And my radius of the moon, you got to be really careful here. This is the distance. Now, why do you got to be careful here? Very good. It's in kilometers. So what do you got to change this to? So that's 1.74, not times 10 to the third. It's 10 to the sixth. Because there's 1,000 meters in every kilometer. So you just add 3 zeros or you add the exponent of 3. Shoot. So that gives you meters here. Not kilometers, but meters. So let's plug everything into the formula. M1, M2, all divided by B squared. And Alexis, what are you going to put in for G? Very good. 6.67 times 10 to the negative 11th. Oh, wait a minute. Did I forget F? Did I forget the F here? No, that's what I'm trying to find, right? What are you going to put in for the mass of me? Very good. 100 kilograms on a good day. It's after I get done doing my P97 and a half workout. And then, I know, I'm almost up there. And then finally, you're going to put in the mass of the moon here of 7.35 times 10 to the 22nd-ish. And divide that by the distance of 1.74 times 10 to the 6th. Now, what did I forget to do? Square it. Good. And I love you, Joe. What'd you say? Now, that's how many newtons I weigh on the moon is 161. On Earth, I weigh 980. So since the moon is about 1/6 the size of Earth, I weigh about 1/6 as much on the surface of the moon. And that's all I got to say about that. Have a great day.